Okay, so I think it's a good time to start. So uh, it's Harish. I am a PhD scholar at ISER Mohali, and I will be conducting your live interactions for this course on each Friday from 6 to 7. So today we are going to discuss the assignment 2 uh, of previous year, so that I have already announced in the last live interaction session. So I hope you guys have at least tried some problems and will be looking to give me hints or your inputs. So let me just share my screen. Yeah. So is my screen visible? Can just one of you confirm it?
Yes, sir.
Okay. Thank you, Shalini. Uh, so the first question says, which of the following groups are abelian? And the groups are dihedral group of order 4, sorry, dihedral group of order 8, cyclic group of order 8, the direct product of cyclic group of order 4 and the cyclic group of order 2 and the quaternion group. You can see all groups are of order 8. We need to see which groups are abelian and which are non-abelian. So I hope all of you can answer this question. This is one of the easiest question in the entire assignment. Yes. Is there anyone?
Z8,
Yes.
Z by mode 8Z.
Yes. And anything else? So
Z4 cross Z2.
yes, Z4 cross Z2 is also abelian. Good. So let me write in here. Two. So solution to the why D4 is not abelian. See, we have the presentation of Dn as generated by two elements, say R comma S, uh, such that you have Rn equal to S square is equal to 1. And in addition to that, you also have Rk of S to be equal to S of R minus K, where K is running from 1 to N. Okay, where 1 less than equal to K less than equal to N. Or you can also see, write it like this, that it contains elements of the form Ri S J such that Rn equal to S square equal to 1, Rk and this all, and we have Ijk running from 1 to N. So this is a presentation for Dn, or in fact we have written all the elements of Dn, right? So you can clearly see that if n is not equal to 2, if your n is not equal to Yeah, I should say n is greater than equal to 3, then what happens? Then your Dn is not abelian. Why? Because of this third relation, right? Rks equal to S R minus K. So if you have K get n greater than equal to 3, then that will implies that all elements are not commuting, right? Do you all agree with that?
Yes, sir.
Okay. So next you can see uh, Z mod nz is cyclic and hence it is abelian, right? All cyclic groups are abelian. So Z mod hz is abelian due to this, and in addition to that, product of two abelian groups is also abelian. The abelian groups is abelian. Thus, it is okay to say that Z mod nz cross Z mod mz is always an abelian group. Yes, so that's why Z mod 4z and Z mod 2z is abelian, and their this product is abelian. Okay, so now let's turn our focus to the last option, that was the quaternion group. So going through the same notation as given in your lectures, I can say quaternion group is not abelian because, can anyone give me the answer for it? Why it's not abelian? Any two elements which do not commute?
Because I dot j is k, but j dot I is minus k.
Yes. Thank you, Shalini. So clearly Ij is not equal to Ji, right? It's equal to minus of Ji, which is not equal to Ji, right? So that's why it's not abelian. So the first question was an easy question, so we all can do it easily. Now let's go back, come to the second question. So the second question says, consider the graph obtained by deleting one edge of the octahedral graph. Which of these automorphism of uh, this graph fix the vertex 3? So, uh, do you know what is a graph automorphism? Anyone? Let me write the definition of graph automorphism, then I think you all can easily attempt this question. So, graph automorphism. So, out of this graph, the writing pad is a bit shaky today, so Out of a graph is all elements of Sn such that uh, sigma of I comma sigma of j is an edge in the graph if and only if I comma j is an edge in given graph. Okay, so now we'll go back to the graph again. Here is the graph. So it says all automorphism of this graph which fixes the vertex 3. So if 3 is being fixed, then say where this 4 can be mapped to, 3, 4 is an edge in this graph. So wherever you map 4, there should be an edge from 3 to that point. So 3 has edges with 4, 1, and 2, right? So you can see that the adjacent vertex for 3 is 4 because 3 and 4 have an edge. 1 because 1 and 3 has an edge, and 2 and 3 because 2 and 3 also has an edge. So if 3 is being mapped to uh, just a second. So if 3 is mapped to 3, then where 4 can be mapped to? 3 is mapped to 3. So 4 can be mapped to either 4 or 1 or 2. Do you all agree? And the reason here is simple because 3, 3, 4, 3, 1, and 3, 2 are edges in the graph. So your graph automorphism should preserve the set of edges. That's why whatever element of Sn you take, it should send 4 to either 4 itself or 1 or 2. Similarly, for these 1 and 2 guys, they can, so your automorphism should permute these three symbols, 4, 1, and 2. They can't be mapped to any other symbol because that symbol don't have an edge with 3, right? You all agree to that? Any doubts? Same is true for 1 and 2. Now you see that, so you have 6 options, right? Because your 3 is fixed and you have to permute these 4, 1, and 2. And once you are done with this, you can see what are the choices for 5 and 6. Out of these choices, only 2 will be there that will preserve this set of edges. That I leave to you because it's just a computation. Once you are clear with the definition, you can just uh, compute it of your own. Okay. Is it clear to everyone or anyone has any doubt? Shall I move to the question number 3?
Yes, sir.
Okay. So let's write here that the correct answer is 2. And we can move on to next question. So same here. Now it's given that the automorphism should preserve the set of vertices 1, 5. So here you are given a bit of liberty that your 1 can be mapped to 5 and 5 can be mapped to 1. They are not fixed, but they have to map to each other. Either one is mapped to 1 or one is mapped to 5. Through you need to count those automorphisms. So first your automorphism should be such that it preserves this set, and then it should preserve the set of all ages. So it's a question of the similar nature. So there will be 4 such automorphisms. Now it's up to you. You need to compute and see which automorphisms make sense and which automorphism does not make sense. Okay, so uh, I'm just writing the solution answer in the notes so that you guys can have a look at it. Solution 3, you have 4 choices. Here you have 2 choices. See, just a computation. You just need to check that all automorphisms which satisfies this condition. That's it. There is nothing much in that. Okay. So yeah. Now let's come to the next question. Question number 4. This says let C star with a group of non-zero complex numbers under the multiplication, and phi is a non-trivial homomorphism from Z modulo nz to C star such that x, which is the image of 1, is non-trivial. Then what is the value of this equation? So first of all, the question is clear to everyone. It says that we have a homomorphism from Z modulo nz to C star, and this homomorphism is non-trivial. So phi 1 of x, phi 1 is phi of 1 is not x, that is identity. It's something else, something non-zero, because identity of C star is 1, right? And 1 is the generator of Z modulo nz. So if 1 is mapped to 1, then everything else would be mapped to 1, because if the generator is mapped to 0, then all other elements will also be mapped to 0. So to say that phi is a non-trivial homomorphism, we need that the image of this 1 should not be 1. These two ones are different. This one is the identity of Z mod nz, and this one is the identity of C star. Sorry, this one is the generator of Z mod nz, and this one is the identity of C star. Okay, so it's just saying that the generator is not mapped to 0. So it's a non-trivial homomorphism. And what can you say about the value of 1 plus x plus so x square plus so on to x raised to n minus 1? So anyone has any guesses? You want to comment anything? Any hint? Or
So we can use the property of homomorphism,
yes,
like it preserve operation, like
that we will surely do. What else we can do? Have you ever seen this expression before? Is it equal to some other expression?
yes, it is a standard polynomial. I don't remember the name. Uh,
Standard polynomial. Okay. So just say yes or no once I write this expression, that whether that is true or not. So the solution 4. So if I write this expression as 1 plus x plus so on to x raised to n minus 1 to be 1 minus xn divided by 1 minus x, then is it okay?
yes, this is I'm talking about.
Yeah. So these two are same, right? You can just check, just take this 1 by x here. Okay. Why we are able to do that? Because x is equal to phi of 1, which is not equal to 1. This is okay only when your x is not equal to 1. Otherwise, it will be a 0 by 0 situation, which you don't want. So this you all agree. Now you can use the property of uh, homomorphism. So this is 1 minus pi of 1 raised to n divided by 1 minus pi of 1, which is 1 minus pi 1 raised to n, right? In homomorphism, you can take the power inside. Now here, a word of caution. Here, this multiplication is occurring inside Zn. So here it's not multiplication, it's addition. So your 1 n is actually 1 plus 1 plus 1 plus so on to 1 n many times, right? Because the operation here is addition. Okay, we are writing it as the group notation because we write g star g star g star as g cube, right? So it's due to the group notation we are writing it as 1 raised to n. Okay, so here the operation is n, sorry, the plus, so it is adding 1 n many times. It's n. You all agree?
Yes, sir.
Okay, and what is the value of n in z modulo nz?
0.
0. So it's 0, n is 0. So now can you guess what's the answer? It is 1 minus phi of 0. What is phi of 0 when phi is a homomorphism? It's identity of
1, 1.
it's the identity of the other group, and here the group is complex, group of complex number. So for with multiplication and its identity is 1, so we are having 0. Okay, so this equation is 0 when x is the image of 1 under any non-trivial homomorphism. Okay, so that's an interesting result, isn't it? So let's move on to the next question. How many homomorphisms exist from z modulo 8z to z modulo 12z? Any guesses? There is a formula for it. You all know that formula?
Yes, sir.
What's that?
It is equals to GCD of 8 and 12.
Good. So why others are not responding? These things are uh, very easy. We haven't moved to some tricky questions. These all are basics, right? So I expect more people to answer, but I don't know. Number of homomorphisms from Z mod and Z to Z not equal to, it should be to Z mod MZ is to GCD of n comma n. So this here 4, 8 and 12, these two numbers we have, right? Equal to 4 is the answer. Okay, so let's move on to the next question. Question number 6. It says if n1 n2 are normal subgroups of G, then n1 intersection n2 is also normal in G. It's a true false question, so at least you can use your tukkas, your fluke, true false,
True.
and Yeah, it's true. Anyone else with same answer or different answer? Uh, Priti, are you saying something? I couldn't hear you. No, you can also write it in the chat. You can also write it in the chat if you want. Anyone else? It's easy, right? If N1 is a normal subgroup, N2 is a normal subgroup, then what can you say about N1 intersection N2? It should be straightforward. Let me. So Shalini, you are correct. It's uh, true.
True.
Yes. Let us just give a small explanation to your answer. So let some small n belongs to N1 intersection N2 and G belongs to G, right? So we need to show that G inverse belongs to N1 intersection N2. But this belongs to N1 since N belongs to N1, N belongs to N1 intersection N2, so it belongs to N1 and N1 is normal. N1 is normal in G. And the same thing you can say for N2 also. This belongs to N2 because again N belongs to N1 and N2 is normal in G. So combining these two, we can say that G and G inverse belongs to N1 intersection N2 and hence N1 intersection N2 is normal in G. Okay. Okay. So now let us move to the next question. Which of the following implies that G is abelian? Yeah, something interesting. First one we have already seen. Cyclic.
Yes, sir.
Yes. Second one, every element of G is equal to its inverse.
Yes. Then it is abelian.
What about third?
Third also hold.
Fourth,
No idea about fourth.
so अब एक दो तीन हो गए तो चौथा छोड़ के क्या करोगे? So four, 1, 2, 3, and 4. All options are correct. So first, I have already told you that it's cyclic. For second and third, I will give you the explanation because it's straightforward. And for fourth, you have to try yourself, see some examples where this thing is uh, true or not. And if you are not able to prove it, then we will do it in the next tutorial. Okay. So let's see how the second and third is correct. So option number 7, right? In case of mm, cyclic, it surely holds. And if G equal to Z inverse for all G belongs to G, then what we can say about the group G and whether it's abelian or not. See, for abelian, we need to prove that the AB is equal to BA for GH equal to HG for all GH in G, right? So what we have, mm, G H inverse is equal to GH. Why? Because of this first condition. G is an element of H. Oh, sorry, G and H both are element of this capital G. So for GH also this thing will holds true. And now what is GH inverse? It is just H inverse G inverse, right? So it will be HG again from the same property. So you have GH equal to HG for all G and H in G, right? Thus we have the group to be abelian. Now, what if the third part, if for every two elements you have AB square equal to A square B square. So if GH square equal to G square H square for all G belongs to G, right? So this is also a one-liner. Just write this square, open this square bracket, and you will have this G, and here you have G, G, H, and H, right? Use cancellations, the right and left cancellations. So this G will be cancelled out with this G, and this H will be cancelled out with this H, right? So this will implies again HG is equal to GH for all G comma H in G, and thus your G is abelian. The last one is also easy, but you need a bit more computation to reach to that. But I am leaving it as an exercise for you. Okay, so fourth is an exercise. Okay. Okay, so let's move on to the next question. Now, from here, the real fun starts. The red products. Have you ever heard of this term, red product? Or some people say it as Reed product. Do you have any idea about it? Anyone?
No, sir.
Okay. So semi-direct product you might have seen in the class.
Yes, sir.
Okay. So Reed product of G and H, it has a general definition, but here you can just see, just take it as Reed product of G and H to be G raised to order of H, semi-direct product with H. Okay. So let me explain it with some examples. Then I think it might be more clear to you guys. Question 8. So in our case, read product of G and H is just G raised to order of H and semi-direct product with H. Okay, so semi-direct product is just a set G cross H with an different operation, not just the multiplication. As we see in the product of groups, it it has a different operation. So what does this operation is? I'm just recalling the definition of semi-direct product, and then you will be able to do the next two questions. So we will be looking the semi-direct product and semi-direct product with H. Okay, this notation I am using here. Our n is just uh, g raised to order of h. In general, it's denoted as n semi-direct product of h. So it's just a notation. Don't worry much about it. So for what you need, first of all, n and h are groups. Groups such that h is acting over n through her homomorphism phi. Okay, what does this means? This means that mm, h cross n to n, you have a map sending the tuple h n to sending this to phi of h times n. Okay. It's just a group action. So you have a tuple h comma n. So h is acting on n through phi. What does this means? That phi of h can compute the elements of n. So phi of h can act on n, and that is h phi h of n. Or sometimes we just write it as h dot n. Okay, if your phi is not into consideration or your phi is obvious, then you can just write it as h dot n. Okay, so if you have a group action of such kind, then you can define uh, the semi-direct product and semi-direct product H as the set of all elements H comma n comma H such that your n is from the group n, H is from the group H, and the group operation is I can write the group operation separately. This set with the operation use a different color. Yeah, anyone remember that operation, or I have to write it of my own? If I am having element say n1 h1 and n2 h2, what should be the composition of that? n1 comma h1 dot n2 comma h2 is, see, no need to get the stress that this definition is very weird looking or anything. It's easy to remember the operation and it's very natural. See, in the second coordinate, it's just the multiplication as you see in the product of groups is just H1, H2, the product of H1 and H2. And the first coordinate has to be an element of n. You all agree? Because it's a subset of this set. You can say it's a as a set it is n cross h, right? But when you look at it as a group, then in n cross h you have the multiplication as the coordinate wise multiplication. The operation is just coordinate wise multiplication. While in semi-direct product you have a different operation. But as a set, it's same as n cross h. So this coordinate should be inside your n, right? So whatever you write here, it should be inside n. So I will say just write n1, h1, n2 in this order, n1, h1, n2. Now this h1 is not inside h, right? But if you write it like that, then it will be inside n. What I did, I just act h1 over n2. So it's n1 times the image of h1 dot n2. So this operation you have h comma n is phi h n if it's acting through phi. So it's just a group operation, a group action. So h1 is acting on n2, and whatever the image is, it's going to lie inside n, and you just need to take its composition with n1. So this element will be inside n. So I have seen many times the people are not able to remember this definition, but that definition is very simple once you understand the concept. So in the second coordinate, it's just a multiplication. It's just a group operation over h. And in the second, just write first n1, h1, and n2, and see you have to put this element inside n. So whatever the best choice, act h1 over n2. Whatever is the outcome, it should be inside n. And once you are done, take its composition with this n1, you will again get an element of capital N. So thus this belongs to n cross h. Okay, the definition is clear to everyone. I hope so. Yeah.
Yes, sir.
Okay. So now can someone tell me quickly that what is the order of n semi-direct product with h? What is this order? Can someone see this? See, I told you, as I said, it is same as n cross h, right?
It is equals to order of n into order of h.
Good, Shalini. So it, as I said, it is same, and group operation doesn't do anything with the order of the group, right? Once you are given a set, its order is going to be the same, whether whatever operation you are having. So its order is same as the order of n cross h, and the order of it is same as order of n and h. Okay. Now there was a small confusion in the question. So in general, whenever you write read product, you naturally take this definition that read product of G read H is G order of H, semi-direct product with H. But when H is Sn, then it changes a bit. There is a reason behind it. I'm not going into that due to time constraints, because otherwise I have to explain the entire theory of read product. But you can just take it like this, that whenever your G is read product with Sn, then you take it as G raised to n semi-direct product with Sn. Okay, you in generally you don't take here n factorial, you just take uh, Gn semi-direct product with Sn. You realize the difference in these two definitions. Okay, here it is order of h. So as per the usual definition, it should be z raised to n factorial, because the order of Sn is n factorial. But in case of nn Sn, due to certain regions, we take it to be n. Okay. So now, can anyone tell me what is the order of Z mod 2Z? Uh, Z mod 2Z, the read product with S3. Yes, it's equal to Z mod 2Z, order of Z mod 2Z raised to 3. Here n is 3. Semi-direct product with S3. Okay, and it is equal to the Z mod 2Z, order of Z mod 2Z Q is to S3, because as I said, they are same. Now it should be easy, right? What's the order of it? Someone see, this live interaction is for you guys. It's not a class so that I am dictating and you all are listening. You should be interacting with me, no? Yes, sir.
48 it is.
Yes. Salini, you are correct. It's 48. It's just 8 into 6, which is 48. Okay. So answer is 48. Now this solution 9 is a bit tricky, and it needs the definition of read product to be understood uh, very in a very good manner. So you can see the answer is this, but I will just say, okay, I can just tell you what is the action you can take here, and then you can try, because it will take some amount of work. It's not an straightforward question. It will take some amount of work, but if you are able to realize what these notations means, then I think you should be able to do it once you spend some time. Okay, so I am just giving you the meaning of these notations, and then you can try it of your own. Solution number 9. First of all, this should be clear that what is G read product of Z raised to n. I am taking Z mod n Z. In the question, we are just given uh, Z2, but let's see this definition for n. So it's G semi-direct product with G raised to n. Okay, the order of Z mod and Z. Semi-direct product with Z modulo and Z. So as per the definition, when we are writing n semi-direct product with H, we need that H must be acting on n through some group action. So what is the group action? The group action is Z mod nz cross G raised to n to G raised to n is such that here you are having some alpha, and here a tuple G1 comma G2 comma G raised to n Gn, sorry, it's just the multiplication, just the power action. You have G1 comma G2 comma G raised to n Now here the group operation is just a product because you are having G raised to n. So it's a product group of groups. So it is G1 raised to n, so on to Gn raised to n. Okay. So this is the definition. Uh, so we are running out of time. If you guys agree, then we can continue with the solution of this question. It's an interesting question, right?
Yes, sir.
Okay. So what is the inverse of h comma what notation we are using? N and h, right? NH inverse in n semi-direct product H. It was a exercise in your lecture notes, I guess. So does any one of you is able to compute it? What's the inverse? I'm just writing it. You guys should be able to verify it. It's uh, your H inverse dot N inverse. H and N are looking similar. Don't get confused. And the other element is H inverse. See, this coordinate is easy to guess, second coordinate, because here you are just having multiplication as the product operation, right? So you want that if let's say N2 H2 is the inverse of N1 H1, then their composition should be equal to identity, right? So when this composition is equal to identity, that is 1 comma 1, when H1 and H2 is equal to 1 and this is equal to 1. So H1 H2 is 1, that means that H2 is equal to H inverse, right? Second component is easy to compute, and in this component also, here also you can see uh, that you need the value of N2. So once you put in place of N2 H1 inverse N1 inverse, what you will get? Your N2 was H1 inverse N1 inverse, right? In place of N2, if you put H1 inverse N1 inverse, then use the compatibility of group action. You will have H1 inverse acting on N2. That means identity acting on sorry H1 or but it's better that I write it here. It might be going. Uh, see, so you have N comma H times its H1 inverse N1 inverse. This is dot. Okay. And it is H1 inverse. You use the definition of semi-direct products. It's just it is in the second coordinate. It is just a multiplication of this first the last coordinate of the first tuple, and in the second coordinate of this second tuple. So it's just H times H inverse times H inverse. So you get identity here, and in the first coordinates you have N, and then I told you that the N, H, and what these three, first, two, and three. You write it in the same line and then put a dot in between. So H dot this thing, right? H inverse dot N inverse, right? As per the definition, written it so far. It's buddy, so it might be feeling alone. So let's write it together. H inverse. Okay. So now it is N and then H inverse dot N inverse. by the compatibility of group action, G dot H dot X is GH dot X, right? So it's H inverse is identity, and this is N times 1 acting on N inverse, right? And 1 acting on N inverse, the first axioms of group action says identity will fix everything. So it is just N inverse identity, which is identity comma identity. Yes, so you get the identity of this semi-direct product. So you all agree that this is the inverse.
Yes, sir.
Okay, so now you have inverse, you have the definition of the group action, you have the definition of semi-direct product, so you can compute what is uh, yes. So the notation here is also a problem. So G comma G 0, and let me just write the notation. X is your G comma 0. It's not like a raised to 0 equal to 1. Okay. So see, this is an element of G square semi-product. This is an element of G square semi-direct product with Z cross Z2. Sorry, Z modulo Z2. Because G semi-direct product, G rate product, Z and Z is G and semi-direct product with Z mod and Z. So if N is 2, then it's just G square semi-direct product of Z mod and Z. So it should be a 3 tuple. Okay. So it belongs to G semi read product with Z mod 2Z, and that is same as G square semi-direct product with Z mod 2Z, right? So it should be a 3 tuple. Yes, so it's actually Z comma G comma 0. So you can see it's a 3 tuple. It's an element of the set G cross Z mod 2Z, but the group operation is different. So G is this, and your X is this, Y is Y1 comma Y2 raised to 1. So it is Y1. It's just a notation. They are denoting it with some different uh, notation. That's it. But you can easily guess that what this notation should be. It is Y1, Y2, 1. Now you can compute what is X, Y, X inverse. Just again, I'm giving you a word of caution that don't compute it as you compute as in the product of groups. It's not uh, same as the product of groups. Here, the group operation is from the semi-direct product Y, X, Y inverse. Here, I'm also writing it here. The group operation is from G square semi-direct product with Z mod 2Z. Okay. So I'm just writing its value uh, by using the group operation. You can see that whether I make sense or not. So it is first we have to put Y, so it is Y1, Y2, then 1, then we have to put X, this is G, comma G, comma 0, and then what was the inverse of N comma H? Your N here is Y1, Y2, the tuple Y1 comma Y2. Okay, so it is the inverse of h first, and your h is, so inverse of, it is 1 inverse of 1 acting on the tuple y1 comma y1 comma y2, right? H1 dot n1 inverse. So its inverse, this inverse is in group, and that is in the second, it's just H inverse. So it's just 1 inverse. Okay, you all agree to that? Any confusions? This is the most interesting question in the entire assignment sheet, so that's why I'm giving it more time. And that will clear all your doubts regarding this semi-direct products. If you understand this question clearly, then you should be able to deal with the problems related to semi-direct products. So one inverse, here this inverse is in the group H, which is here Z2. So what is the inverse of 1 in Z2?
1.
Yes, 1. And 1 acting on Y1, Y2 inverse. Here the inverse is in G, which N, if you are going with the definition, N direct semi-direct product H. So what is uh, the inverse of Y1 comma Y2 inverse here? The inverse of Y1 Y2 in G square, the product. Yes, it's just Y1 inverse comma Y2 inverse. Okay, its inverse is in inverse in G square, and this inverse is in inverse in, I will write more clearly in the notes, don't worry. Inverse in Z2. Okay. And again, one inverse is 1. Okay. So, one acting on this tuple, I told you that operation is, where that operation went? Operation is just alpha acting comma G1, G2, so to Gn is G1, G2, Gn raised to n. So here we are having alpha. I made a small mistake. Sorry. I made a small mistake in a typo in above. It is G1, so it will be Gn raised to alpha. Otherwise, alpha would have no role to play, na? So it's now the group operation must be, group action should be clear to you. It's G1 raised to alpha, so into Gn raised to alpha. Okay, so yes, can anybody tell me the final answer? Okay, just let us keep these two as it is. At least we can simplify the last one. One acting on this is y1 raised to minus inverse raised to 1 and y2 inverse raised to 1. So it will be just y1 inverse comma y2 inverse, right? By the definition of group action we have seen above.
Yes, sir.
Yes. Okay. So this computation, will you be able to do, or you want me to finish it? Okay, let's do it fast. See, this is our N1, this is our H1, This is our N2 and this is our H2. So we will first put this tuple y1 comma y2 as it is and see how this one acts on the tuple g comma g. I'm just using the definition of semi-direct product. It's uh, just that's what we did now. We just put first uh, n1 as it is, h1 we act on n2, right? And then we multiplied h1 and h2. So 1 dot 0. So this is the outcome of first two triples now. Uh, uh, and in this and at the end we have this. Okay, so let's quickly finish this. So it's see if one will act on g comma g, then it will be g comma g raised to 1. That will again be g comma g, and then g comma g multiplied to y1 comma y2, it will be y1g comma y2 of g, right? These two should be in the first two tuples. You all agree?
Yes, sir.
Okay, at least one person is awake. So 1.0 is 0 in Z2, and here you have y1 inverse comma y2 inverse. This is a very good question. It will clear all your doubts regarding to semi-direct products once you understand this question, because here we are dealing with three tuples. For the first two coordinates, it's the product, and in the combining those two coordinates with the third coordinate, it's the semi-direct products. So it's a very good question. So uh, even if you are not getting it here, go and see the recordings and try to understand this question very clearly, because that will clear all your doubts regarding products and semi-direct products. Okay, so now this is your N1, this is your H1, this is your N2, and this is your H2. I'm again putting a bracket here just to make you guys comfortable with the notation. So this is first element, this is second element, this is the first element here, and it's the second element. So it will be y1g. As time is running, my writing is also getting poorer and poorer. So y1g comma y2g. So, and this with 0 acting on y1 inverse comma y2 inverse, and then you have 0.1. Okay, so the last entry, the second entry should be 0. Let's go back to the answer. So you can see the power is 0, right? So the second entry is 0, last entry is 0. There is some y2 y1 inverse. Did we miss something? So it should be x is this, y is y1 y2. So y1 y2 comma 1, and then g comma 0, and then you have right, y1 y2 1, g comma 0, and the inverse of it here is 1 inverse y1 y2. Yes, it should be okay. I don't know why it's not matching with the answer. Maybe somewhere we have done the calculation wrong, but it's going to be the uh, it should be in the same process. You can finish it here. Okay. The second coordinate is matching with the answer. I don't know where we have done the mistake in the first coordinate. because once you apply 0 here, it will be won't contain anything of from y1, y2. Our answer is a bit different from what is the correct answer. Let's write anyway what we are getting. y1g, y2g, and 0 dot y1 inverse y2 inverse is y1 inverse raised to 0 and y2 inverse raised to 0. It's 1 comma 1, and the third coordinate is 0. So we are not having y1 inverse at the end and y2 inverse in the end. Maybe we have done somewhere something wrong, but I will see if any correction is there. Okay. So that's it. I am restating all things of this question again so that you guys can recall. So G reproduct with Z Z modulo NZ is Gn semi-direct product with Z modulo NZ, and the action with which the semi-direct product is defined is Z modulo NZ cross Gn, sending it again this tuple to Gn in this manner. Alpha comma this is G1 G2 so on to Gn raised to alpha, which is G1 alpha so on to Gn alpha. The inverse of any tuple in n semi-direct product H is H inverse dot n inverse comma H inverse. We all verified this. The given number is x. The given variables are x and y. Sorry, the elements are x and y, which is the g comma g raised to 0. It's a 3 tuple, so it means that it's 0 g comma g comma 0, and it means y1 y2 comma 1. So we need to compute what is yx, y inverse. So this is y, this is your x, and y inverse as per the computation above. It's h inverse dot n inverse. So our h was 1 here, so 1 inverse dot y1 y2 inverse, and then h inverse. Okay, so we put it here. Then 1 inverse is 1 in Z2, and y1 y2 inverse in G is y1 inverse comma y2 inverse, and y1 inverse is again 1. So when 1 acts on it, it gives you again the same y1 inverse y2 inverse comma 1. Then we use the definition of semi-direct product to say that this is same as y1 comma y2, and 1 acting on g comma 1 dot 0. The third element is, we write it as it is, and then by the definition, this 1 dot g comma g is g comma g, and when g comma g is multiplied to y1 y2, it's y1 g y2 g. 1 dot 0 is 0, and then here we have y1 inverse y2 inverse comma 1. Again we use the definition of semi-direct products. It says that y1g y2g, and then 0 acting on y1 inverse y2 inverse, and then here 0 dot 1. So it's y1g y2g, and here 0, here 0 dot this means 0, this tuple raised to 0, and that means the identity 1 comma 1. So once we did this, it is y1g y2g comma 0. So maybe the answer is not correct, but whatever we have done, that's okay, that's correct. So I will just quickly give you the hints for next questions, and then we will stop. So question number 10. I will take hardly 10 to 15 minutes more. If you want to finish me all these questions, then otherwise, if you want to leave, then you can leave. But it's better to understand these questions because some of them are really good questions and important questions. So this 10th question is what can be the order of the center if the order of G is p square. So even without looking at the options, you can easily guess that what should be the order. See, first of
P
all,
square.
the order is p square. Yes. Did you look at the solution? The answer was also there. Or you know how it is p square.
Yes, sir.
Why it is p square?
Because every good group of order p square is a billion, and if G is a billion, then G equals to ZG. So their order should be same.
Yes, Shalini, very good. So order of G is p square. This implies that uh, G is abelian, and that implies G is equal to the center of G, and thus the order of ZG is p square. Okay. Yes. So the next question is of the modulo. Consider the system x uh, uh, congruent to 2 modulo 3, x congruent to 2 modulo 5, and x congruent to 4 modulo 7. So what is x congruent to modulo 105? So see, what is 105? 105 is just the product of 3, 5, and 7. 3 into 5 is 15, 15 into 7 is 105. So mm, the best way is to use the corollary of Chinese remainder theorem. I'm not stating it here, uh, but you can go and have a look at it. The answer is 32 here, and you can just verify the 32 congruent to 2 mod 3. Okay, it's uh, 30 is divisible by 3, then 30 is also divisible by 5, and 28 is divisible by 7. And you can check that whether there are more solutions to it or not. Okay, between 0 and 104, I can tell you there won't be any other solution. So just use Chinese remainder theorem, and the answer is 32. Okay, then 12. In how many ways can the elements x, y, z be chosen from among the quaternion group such that x, y, z equal to identity? It's just a counting problem. You need to see all the combinations such that x, y, z is identity. You can use the composition table of quaternion group and come to it. There would be 64 choices. Uh, I can give you a hint of such that it will reduce your effort. First, put x to be identity. Then, if yz is if xyz is identity, then y has to be the inverse of z. Okay, so put x to be identity and vary y over g, and then z would be just the inverse of y. So you will get 8 choices in this way. And secondly, reverse the process. Repeat the same thing with y to be identity, and repeat again the same thing with z to be identity. You will get some choices, and just have a look that whether there are some other choices available or not. Total number of such tuples would be 64. Okay, 13 is also an interesting question, but so I will just give you some hint. So H is a subgroup of the group G, uh, which is a quaternion group, and we need to find what are all characteristic subgroups of this H. So characteristic subgroup is a subgroup which is fixed by all automorphism of G. Okay, and we need to see how many such subgroups are there in quaternion group. Okay, so two subgroups are always uh, characteristic for every group. You all agree? What are those two?
Yes, sir. Trivial subgroups that.
Yeah, trivial subgroups. So solution of which question is this? 13, 13. Yes. So 1 and G are always, let change the color, characteristic, right? And what else? Uh, I'm writing this quaternion group G as plus minus 1 plus minus I plus minus J plus minus K. Okay, and you can see that the more map from G to G, sending I to J, J to K, and K to I. Uh, let's say this is phi 1 and this is phi 2. So for phi 2, you can see, so we can send J. Let's start with I again. I can be mapped to K, J can be mapped to I, and K is mapped to J. So these two are automorphisms. Okay, you can verify them. They are automorphisms. Uh, so let's say H is characteristic. One more thing you can see. See, minus 1 has order 2, right? And there is no other element of order 2. So f of this phi of minus 1 should be minus 1 for all phi in automorphism of G. All automorphism of G should fix this minus 1, right? Because there is no other element of order 2.
Yes, sir.
Okay, so two elements are always fixed, 1 and minus 1. So 1 comma minus 1 is also characteristic, is also characteristic, right? Now there are 6 more elements remaining. So let's say I choose any, let's say this, that H is characteristic, and small I belongs to H. Then as H is characteristic, so what can you say? And H is also a subgroup, characteristic subgroup. Then first of all, the group generated by I, this will implies the group generated by I should be inside H. You all agree? Because H is a subgroup, I belongs to H. So all powers of
Yes.
I should be there. So what you get? 1 minus 1. I should write it as powers of I. I square is minus 1, and then I cube is minus I, and I4 is 1. So this should be subset of H. You all agree? So
Yes, sir.
first of all, this H must contain these 4 elements. Now we are given that H is also uh, characteristic, right? So since H is characteristic, Therefore, even phi 1 is enough. We define phi 2 uh, unnecessarily. Even phi 1 is even enough. So phi 1 of I must also be there inside H. But what was our phi 1 of I? Phi 1 of I was J, right? So J should also be there inside this H, which implies J also belongs to H, right? And once J is there, this would implies I dot J is that is equal to K should also be there. And as J is there, minus J must also be there, right? And K is there, so minus of K should also be there. This implies that uh, uh, J, K, minus of J and minus of K is also inside H. And what does this means? Your H is nothing but G. So there are only three possibilities. First is 1, second is 1 and minus 1. And as soon as you take a characteristic subgroup containing any I, J, K, minus I, minus J, minus K, it will force you to, the characteristic property will force you that your H should be G. So there are just three characteristic subgroups. Okay. How many conjugacy classes are there in S3? So there is a straightforward formula for computing conjugacy classes of Sn.
Yes, sir.
That comes through the nature of conjugacy classes, because whatever cycle type you take and you conjugate, you take the conjugate of it, you will get the same cycle type again. So the partition of n is always fixed, always preserved under conjugacy in Sn. So number of conjugacy classes, uh, conjugacy classes of Sn is same as the number of partitions of n. Partition of n. Okay. So here uh, n is n equal to 3. So 3 can be written as partition of 3 is 3, 2 plus 1, or 1 plus 1 plus 1. These three partitions are possible, right? So this will implies number of conjugacy classes, or better I should give it a notation. Let's say this is cardinality of, or let's say this number is small c. So we have small c to be just 3. Don't get confused that the answer is 3 because n is 3 here. Okay. If you go to higher numbers, this partition increases very rapidly. So the number will increase. So it's not because n is 3. It's because 3 has 3 possible partitions only. 3, 2 plus 1 and 1 plus 1 plus 1. Okay. Now let's see the last question as well. So let R denote the set of bijections from R cross R, which preserves the distance between points and take integers to integers. Consider the translations automorphism T from R to R given by Tx going to x plus 1, and the reflection R given by Rx going to Rx is minus x. The subgroup generated by R and T is isomorphic too. So if you have seen the definition of D infinity, then there also we have the same thing. the definition of G infinity is just Z semi-direct product with S2. Okay, where identity acts on the mm, uh, Z2 as sorry, Z semi-direct product with S2. So where identity permutation acts on an integer in the usual way, that identity will fix the integer, and the cycle 1 comma 2 will send an integer m to minus of m. Okay, so it's also doing the same thing. You can see that it will be isomorphic to that. That won't create any problem if x is just translating by x plus 1. You can see y, and you should be able to define an automorphism from this to d infinity. And here, see, it's written z semi-direct product with z modulo 2z. Z modulo 2z is same as S2, because S2 is also of order 2, and all groups of order 2 are cyclic of order 2, right? It's they are isomorphic to Z modulo 2Z. So there would be two options, correct options: Z modulo 2Z, sorry, Z semi-direct product with Z modulo 2Z, which is also denoted as D infinity, the infinite dihedral group. So I'm not going into the definition of D infinity, but it's already there in the notes. You can revisit your notes, and you will be able to define an automorphism very easily, because the nature of reflection is same as the nature of this R is acting same as this 1 comma 2, and this translation is doing nothing but just sending x to x plus 1. So as this is a set of real numbers, so its automorphism group will be isomorphic to Z semi-direct product. The subgroups generated by R and T will be isomorphic to the Z semi-direct product with Z modulo 2Z, and that is Z modulo Z semi-direct product with S2, and that is D infinity. Okay. So with this, I think we can close the session now. If you have any quick questions regarding any of the above questions, then you can ask. Yes, any questions?
No, sir. Thank you so much, sir.
Okay, thank you, Shalini, for your response. And I request others that please come with at least some amount of preparation, so that you can also participate in the discussion and you can also respond. Uh, okay, we will meet again in the next on next Friday at the same time, 6 to 7, and we will be solving assignment number 3.